So we can take a look at meteorites. We can examine that soluble organic material that's within them and kind of get that snapshot into the origins of the universe, the origins of the solar system, and kind of see where did everything come from? How old is it?
Hello, I'm Emily Schneider from the American Chemical Society, and welcome to this media briefing from ACS Spring 2023. If you've ever seen a shooting star, you might have actually seen a meteor on its way to Earth. Those that land here are called meteorites and can be used to peek back in time into the far corners of outer space or at the earliest building blocks of life. Today, scientists report some of the most detailed analyses yet of the organic material of two meteorites. They've identified tens of thousands of molecular puzzle pieces, including a larger amount of oxygen atoms than they had expected. We're joined today by Alan Marshall and Joseph Frye-Jones from Florida State University and the National High Magnetic Field Laboratory. Thank you for joining us.
Thank you.
Thanks for having us.
So, what were you trying to find out with this research?
So we were wanting to investigate the organic material that's present in non-terrestrial materials. So meteorites, lunar material. Um, a lot of the studies into meteorites and lunar soil happened during the space race back in the late 60s, early 70s. The instrumentation wasn't anywhere near it is today. So there's been a lot of technological advances, new instrumentation. FTICR mass spectrometry that we're using now wasn't even invented until 1974. So a lot of this research was done before the technique we even invented, or I guess Dr. Marshall invented. Um, and we've come so far since then. The 21 Tesla FTICR mass spectrometer here at the National High Magnetic Field Laboratory is the highest resolution instrument in the world. And we can look at things that others simply can't. We can investigate those complex mixtures that others can't. So we wanted to look at the organic composition of these meteorites.
And then, why is this an important thing to know?
So, like I was saying, a lot of the studies that have happened before were in the late 60s, early 70s. And so there have been some studies since then throughout the decades. They've been primarily focused on specific compound classes like amino acids or aromatic hydrocarbons, polycyclic aromatic hydrocarbons. So they've been very targeted in their analysis. But with the high resolution mass spectrometry that we have here, we can look at a very broad, at the organic material in a very broad sense. So instead of targeting, we can analyze all of it as a whole. And so when we can do this, we find that it's a very complex mixture, more so than a very targeted analysis can show us.
So, then how did you investigate these meteorites, these complex mixtures?
So first we had to pick which ones we even wanted to look at. So the first meteorite we chose was Murchison meteorite, which fell in Murchison, Australia in 1969. It's one of the most studied meteorites on Earth because of how well that it was preserved and how much material was collected. Over 100 kilograms was collected of it, and it experienced very little terrestrial contamination since it was collected so soon after falling. So there's a lot of literature out there on this meteorite that we can kind of compare our results to a little bit to make sure that we're on the right track with extracting organic material. The second meteorite we chose was Aguas Argus meteorite, which fell in 2019 in Costa Rica. So it's relatively new meteorite that very little data has been published on and no high resolution mass spectrometry data. Because as we all know, COVID hit and caused a lot of problems when it came to research getting back into the lab. So first picking those two meteorites, then we went into the lab and basically we take each fragment, we break it into smaller fragments with a hammer, and take those smaller pieces, and we put it in a mortar and pestle with a little bit of organic solvent, and we crush it up into a fine powder, much like you do with herbs in the kitchen. Um, we can take the liquid solvent off of the pieces that we've crushed. We can then dry it down, bring it up to a known concentration, and inject that into the mass spectrometer for analysis.
Great. And then what did you learn?
We've learned a lot. We've learned just how complex it is. Like we have an idea as to how the complexity based off of previous studies, but I didn't realize just how complex these non-terrestrial materials from outer space are. Um, this spectrum here is from the methanol extraction. It's got over 29,000 peaks present. Each peak can be assigned a molecular formula. Each formula corresponds to dozens of different compounds. So potentially hundreds of thousands of species present in just this one spectrum, hundreds of thousands of different compounds. And you can kind of see this complexity when you zoom in to this little inset at just one mass at 501. You have 66 peaks that are present here. And that tallest peak that's present, you can see the molecular formula. We can assign that as O7 Na1, right? We can then take those molecular formulas, combine them into what are known as heteroatom classes, and kind of plot out the trends and see what the composition of these the organic species are, and kind of learn the different trends that are present.
And for every molecule, every time you make a ring, you lose 2 hydrogen. Every time you make a double bond, you lose 2 hydrogen. So if we have the chemical formula, we can count the number of hydrogens versus carbon, and then we get to measure the number of rings and aromatic rings and double bonds. And the reason we use this instrument is the magnet spreads out the signals much like a prism spreads out the colors of visible light. So the bigger the magnet, the more spread, and we have the strongest magnet in the world for this experiment.
So what's the significance of these findings?
So we're able to investigate the organics of these materials from outer space that are, well over 1 billion years older than Earth. We're getting this sneak peek back into the origins of the solar system. Murchison meteorite has been clocked at between 5.5 and 7.5 billion years old, which is almost, at 7.5 billion years old, that's almost 3 billion years older than the solar system itself. So it was floating out in space far before our solar system was even a thought in the universe. And we're able to take these materials, extract the organic matter that is soluble in our solvents, and analyze them and take a look at those complex matrices that basically exist out in space that never even thought would have been there. Especially when you consider hydrogen is the most common element, the lightest element. It's the most prevalent one in the universe. And we've got so much more than just hydrogen.
Well, thank you both so much for sharing your research with us.
Thanks for asking about it.
Be sure to check out our other media briefings for ACS Spring 2023, which will be posted throughout the meeting at www.acs.org/ACS Spring 2023 briefings.